So as I was saying earlier, briefly, what I'd like to talk about here is learning to learn, or actually meta-learning, as it's also known, for in general and at a high level, but also in terms of applications to communication systems. And I think the general message here that I'll try to convey is that when it comes to using data-driven design methods for communication systems, meta-learning often provides a more suitable framework than conventional meta-learning. And this is because it leads to solutions that can be more data efficient and also more computationally efficient. In some cases, just using conventional machine learning leads to solutions that are just not feasible in terms of the amount of data and complexity that is needed. But meta-learning instead can address these limitations. As I was also saying, these slides are quite high level. And if you have attended the nice seminar that was organized by Technion a couple of weeks ago, this is essentially the same talk. So feel free to interrupt me at any point and ask me to maybe be more specific about certain aspects, or if you have any more detailed points that you would like to be clarified, I'm happy to do that. Okay, this is joint work with Sang-Woo Park and Junyu Kang, who are both at KAIST, and Sharu Jose and Heryoung Jang, who are in my group at King's. And yeah, so I think first maybe we can look up in the dictionary to remind ourselves what meta means. So meta is quite commonly used in popular culture these days, and it just identifies things that refer to themselves, right, in a self loop. So, they can, meta can refer to a novel like this one by Italo Calvino, which is about the reader reading the novel. It can refer to of course, to the art of M.C. Escher, which is clearly self-loopy, and to a movie like Being John Malkovich, which is about, the actor, ostensibly about the actor starring in the movie. And, meta-learning is about learning how to learn. So it uses learning to improve the way learning itself is carried out. So again, we have this self-loop. And so in the rest of the talk, I'll try to motivate first why using meta-learning for communication systems, to design communication systems may be a good idea. Then I'll provide a high-level view of description of what meta-learning does, and especially in comparison to other learning frameworks. And then I'll just zoom into one specific application. And for that application, I'll cover algorithms, some specific algorithms that are state-of-the-art at the moment on meta-learning algorithms. Okay, so motivation. So I have chosen two examples to motivate the use of meta-learning. And these two examples, I've chosen them because, in my opinion, they exemplify the two cases in which using machine learning, or anyway, a data-driven approach to design communication systems is sensible. That is when we have either a model deficit, right, or we have an algorithm deficit, if we were to follow the conventional engineering design approach. And so to exemplify the first type of situations where we have a model deficit, consider a case where we have, IoT devices communicating to a base station, sending short packets, sporadically maybe. And so each packet has just a few pilots. And these pilots are typically used in a conventional, model-based design approach. These pilots would be used to identify the parameters of a model that would describe the propagation between transmitter and receiver. So we would trust the validity of this model. We would use the pilots to estimate the parameters of the model, and then we would use, we would design optimally a decoder or a demodulator that relies on the validity of that model. Now, machine learning can be, or data-driven approach becomes useful or potentially promising when there is a model deficit. So we don't trust as much the model that we have for the propagation between transmitter and receiver. For instance, in the case of this particular example, if the devices have some hardware imperfections that are hard to model, and for which, again, we don't have reliable models. The issue here is that if we try to use machine learning for designing a demodulator or a decoder for, let's say, any one of these devices from which we are receiving. We just don't have enough data, pilot data, to, from scratch, train a demodulator or a decoder. And so we have a sample complexity issue. We don't have enough samples. And so the question is, can we still use machine learning to design the receiver? So the second example that I like to use to illustrate the second type of scenarios in which machine learning makes sense is when we have an algorithm deficit. Okay, so to illustrate it, consider now the problem of training end-to-end a transmitter and a receiver. Now we have a good channel model that we trust, so we can generate as many samples as we like. We can simulate the channel. So we don't have a sample complexity issue any longer. We can just generate at will samples. But the issue here is that we may have a good channel model, but we don't have ways to design by hand through optimization an optimal or almost optimal transmitter and an almost optimal receiver. And therefore, we would like to see if we can use a data-driven design approach to come up with a transmitter and receiver that work well for this channel model that we have, for instance, for this simulator of the channel that we have. So the issue here is not one of sample complexity. Again, we can generate data. The issue is that anytime this channel model changes, so we have changes in the setting we are operating on, and so we need to change the channel model, we also need to retrain transmitter and receiver. And so this can be too complex in terms of just the time it takes, in terms of number of iterations, for instance, of a learning algorithm. And so the second question that we pose here is that is whether we can use, again, machine learning tools when we are only allowed to do just a few iterations, say, of gradient descent, or stochastic gradient descent, anytime the channel changes, right? Anytime the configuration of the system changes. So I'd like to argue in the next, basically in the rest of the talk, that meta-learning gives a way to answer positively, of course with some limitations, to both of these questions. So we can use machine learning even when we have issues of sample complexity, of iteration complexity, but we should do it again by leveraging meta-learning, the meta-learning framework instead. Okay, so let me just try to describe at a high level how meta-learning works. And again, if you are familiar with meta-learning, this may be kind of a repeat, but it may be useful to others. So first of all, meta-learning is not a new concept. There was an edited book published by, as you can see, some quite famous authors in the 90s, at the end of the 90s. And this contains already, still very useful material. And more recently, there has been renewed interest in meta-learning, in large part motivated by the publication of this paper, which essentially shows that you can use gradient descent, or in any case, you can use automatic differentiation libraries to implement meta-learning in a very efficient and model agnostic way, so quite generally. And if you haven't seen this paper, I'll describe the main technique proposed in it later in the talk. So again, how does meta-learning work? And in my opinion, in order to really understand it, it's useful to take a few steps back and just review how conventional machine learning works and how the limitations of machine learning are typically handled in a lot of the papers on wireless, or in any case on communications. Okay, so in conventional machine learning, the starting point is always that of selecting an inductive bias, right? You select a model class, for instance, you select certain class of neural networks with certain number of layers and so on, hidden neurons. And then you select a training procedure. You may select, SGD with a certain learning rate, and maybe Adam or any other trick of the trade. And so this is fixed in principle, right? And then you collect data. And just to make it visually appealing, or anyway more clear, here I'm considering the problem of designing a classifier between images that represent backpacks and images that represent flowers. And of course, you can think of the problem of decoding or demodulation as one of classification, right? Classifying zeros from ones and so on. So this is just a way of visualizing the problem. Okay, so you fix the inductive bias, you collect training data for this particular task or any task. You apply the inductive bias, that is, you apply the training procedure, which is typically, again, an optimization procedure. And this training procedure identifies a model parameter that identifies, in turn, a specific model in the class you have chosen. So, for instance, the weights of this neural network. And in this case, the model parameters define a classifier in the space of the data. And then to test if this model works well, we need to check that it generalizes, right? It generalizes outside the training data. So in particular, to test data drawn from the same distribution, right, of the training data. So we take more images on backpacks and flowers, we apply the classifier, and we check the test accuracy. And, and we see how the model works and how it has generalized. So again, the issue in using this approach to communications, as seen in the two examples that I talked about earlier, is that you generally this training procedure, this approach needs to be applied from scratch anytime the configuration of the system changes. And so one needs enough data for the new configuration and also enough training time for the new configuration to identify a well-performing model parameter. And so these are the two issues that we discussed before. So in many papers, including in communications, the way one gets around this problem is to use what I call here joint learning. So here, the idea of joint learning is that, instead of training one model for one configuration, let's train one model that works well across multiple configurations. For instance, in the case of wireless channel, we may collect data for multiple channel realizations and then try to identify one model that works well on all these realizations, right? On average over all the realizations. So visually here, what we can do is, instead of designing, again, a classifier for one task, we collect data from multiple tasks, multiple channels, right? For instance, here we have the task of distinguishing backpacks and flowers, but we can also now add to that, to this data set, images that represent crayons and mugs. So now we have two tasks whose data are pulled together to define a bigger data set. And so now, for instance, we can label all the flowers as ones and all the backpacks, all the flowers and mugs with ones and all the backpacks and crayons with 0. And then we consider this as a big data set on which we can again apply the inductive bias, obtain a classifier, and now again we have a single classifier which we hope to work well for all these tasks that we have pulled together. And then to test if we have done a good job, what we can do is we can hope that if we then take one of the tasks we train the system for instance, backpacks, crayons and mugs, and we take test images or test data for that task, we hope that the classifier we have selected generalizes well for that task, or in general for any other task selected at random from the pool of tasks we have considered. So this approach is quite commonly used in many papers. And it seems to solve both problems, right? Because even if you have few data points for each task, for each configuration, overall, the overall data set may be sufficiently informative to obtain a decent classifier. And we have also, it seems that we have also solved the complexity issue because we only need to train this model once for all these tasks. And so the complexity is amortized, right, across all these tasks we are considering. But, if one thinks a little bit more deeply about this problem, in fact, joint learning has two clear shortcomings. One is that there may not be a single model that, for instance, a single decoder that works well no matter what the channel realization is. And the second is that there is nothing in this procedure that enables the model we learn to adapt well to a new task that we have never observed. Right? There is nothing here that enables adaptation on a new task. Okay, so basically meta-learning is a way to deal with these two shortcomings, with these two limitations of joint learning. the fact that there may not be a single model that works well, and the fact that we would like the model to be able to adapt to a new task. Because in communications, once the configuration of the system changes, we typically get data from the new configuration, right? Pilot from a new channel realization. So we should be able to use that data to adapt the system, the model, to that new task. And so meta-learning, again, tries to do that as follows. The starting point is the same as for joint learning. So in terms of data, the requirements are the same. So we have data from multiple different tasks, again, backpacks and flowers and crayons and mugs. The first difference is that we do not create a single data set, a single task in which we pull together all these data, but we keep these data sets as separate. So we treat each system configuration as an independent, different task, which of course all these tasks are related in some way. These are all binary image classification tasks, but we keep them as distinct, right? We don't try to find a single model that in a way solves all these tasks at the same time. And so we have, we call all these data sets as meta-training data. So this is the data that we use for meta-training. And as you can see, typically for each such task, we will have training data and test data for each one of these tasks. And we use this meta-training data, again, not to identify a single classifier, but to, working at a higher level of abstraction to identify an inductive bias. And again, identifying an inductive bias means identifying a specific model class, for instance, a specific configuration of hyperparameters that defines the neural network, or more commonly, a training procedure. So essentially an optimization scheme. Okay, so we use, again, this meta-training data, not to identify a model parameter, but to identify hyperparameters, to identify an inductive bias, for instance, again, to identify a specific training procedure. And I'll give you some examples later, but you can think, for instance, to identify a learning rate, to identify a specific way of applying stochastic gradient descent, and so on. So we're really learning by using meta-training data. We are not learning, but we are learning how to learn. We are learning how to optimize. We are learning how to adapt. And this is in the sense that this inductive bias should be selected in such a way that when we apply it separately on each one of these tasks that we have, so we apply, this inductive bias, this particular optimization procedure, we apply it on this task and on this task, but again, separately. The models that we obtain separately from each task work well in the sense that they generalize well on the corresponding test data. So again, what we're trying to do here is to learn how to adapt, learn how to adapt for all of the tasks that we have in this meta-training test data. And we would like in particular that this adaptation is effective, even if we have just a few examples, so limited data, limited samples, training data, and or limited iterations that we can perform for each one of these tasks. Okay. So again, we're trying to learn how to effectively adapt using few data points or using few iterations on each one of these tasks. And so because we have built the system to adapt, we can then test it, what we call meta testing. We can meta test it on a new task, of course, related to the ones we have meta trained for. For instance, we may want to now distinguish, furniture and cameras, and maybe we have just a few examples of furniture and cameras. And now we give the inductive bias, right? We give this training procedure we have meta trained, this training data, and we hope that with just few data points or just few iterations, the model that is trained can perform well on test data for that task. So now we can go into test it on new images of furniture and cameras, and we hope again that this model has generalizes well by using this meta-training inductive bias. So in summary, what we are doing here, we are using related tasks to transfer knowledge to a new task. And this transfer of knowledge takes place in the form of hyperparameters. Okay, and again, if there are any questions, I'm happy to answer them now. But again, if you have seen this before, this is probably clear. Okay, so I talked about inductive bias, and there are many different techniques, probably dozens of techniques, meta learning techniques that differ in the way the inductive bias is encoded. So there are non-parametric, in which the inductive bias is encoded in features that are extracted from the data in such a way that, again, adaptation can be quickly carried out using just a few data points for the new task. But more commonly, the inductive bias is encoded by the training procedure, so that we may have different ways of using, for instance, past gradients that we have observed. And maybe we can train a neural network, a recurrent neural network, to use these gradients to optimize more efficiently. We can meta-train the learning rate, or as in the paper that initiated this new wave of interest in meta-learning, we can meta-train the initialization that is used for adaptations within each task. And this is a technique that I will discuss in more detail later in the talk. So to conclude this high-level discussion on meta-learning, I think it's useful to compare meta-learning with other learning paradigms which are quite related to meta-learning, namely transfer learning and multitask learning. So in transfer learning, there are two tasks which are very well identified. So, task 1 and task 2. During training, you get to observe data from task 1 and maybe some data from the task 2. And then in the testing, you're going to be tested on task 2. And so the hope is that you can transfer knowledge from one particular task to another particular task, typically having some information about the way in which these two tasks relate to one another. In multitask learning, one is given a certain fixed number of tasks, n, 1 to n, which are very well defined. And these are the same tasks from which we collect data during training and on which we are going to be tested in the testing phase. These are just fixed tasks that are going to be encountered both during training and during testing. And in meta-learning, instead, during training, we are given data from some tasks. And during testing, we are going to be, again, tested on a new task on which we have no information, apart from the fact that it's related to the tasks that we have observed before, right? That it's in some way generated from the same statistics. Okay, so in view of this, in my opinion, meta-learning, as you can probably imagine, is quite well suited for many problems in communications, because, again, the configuration that we get to observe during deployment is one that is related to the ones you have observed before, but a priori unknown. Okay, and so to elaborate on this point, let's focus for the rest of this talk on that first example that I mentioned earlier. And I'm also happy to talk about the second one, but in the interest of time, I have here slides for the first problem, which is also a bit simpler. So remember, in the first example, we just have a simple uplink channel. Devices transmit to a base station, and they take data from some constellation. So we have the symbols S from some constellation. We can assume that maybe the transmitters have some distortion, maybe hardware related, that it's hard to model, and for which we would like to use machine learning. So given its presence, we would like to use machine learning to overcome the fact that we are unaware, we are unable to model this random transformation. And then the signal goes through, let's say, flat fading channel, and noise is added. Now, to use meta-learning, we're going to assume, and I'll get back to this point later, that, the goal here is to just design a demodulator, a very simple problem. So we would like, given the received signal Y, to assign a probability to every constellation point. So this gives us a soft demodulator, right? That gives us the probability of every possible symbol S given the received signal Y, and we are going to use a neural network or another machine learning model that is defined by some parameters phi to define such probability. And we would like to use potentially machine learning, meta learning to train this demodulator. And so for this purpose, we are going to assume that apart from the new device, which we observe at deployment time, at test time, and from which we get some pilots, and for which we want to detect some data symbols. So apart from the new device that we observe at deployment time, prior to deployment, we have observed pilots from other devices, right? So which we call meta training devices here. So I think this is very natural. So we have observed symbols received from other devices that are similar to the devices that we will encounter during deployment. And for each one of them, we have a data set of pilots S and received signal Y. And it's useful to point out from now that meta learning will divide this meta training set into two parts. One part that is used to adapt the models for each one of these devices, and one part that is used to test how well that adaptation has performed. So to test the, to assess, to gauge the quality of the current inductive bias. We'll get back to this point later, but maybe hopefully it's already clear from the discussion that, to the high level discussion that we had earlier. Okay, so now how can we proceed? If we were to use conventional machine learning, we would forget about the presence of this historical data from devices that we have observed before. We would just take the pilots from the new device, from the new channel realization, and we would train a classifier, a demodulator, to classify the transmitted symbol S given the received signal Y. And this is typically done by minimizing the cross entropy loss or the log loss, right? And in particular, one has a certain data set. These are the pilots that you have received from the new device, and you will sum the log loss or the cross entropy loss on the this data set, and you'll try to find a model parameter phi that minimizes this loss. And typically you would want to do that by using stochastic gradient descent. That is by taking a mini batch of samples from the training set and then trying to move in the direction that locally minimizes the cross entropy loss. Okay, this is the standard approach. And it implements the block diagram that, that we have seen earlier. Now, in many papers, this is not done. What is done is to use joint training, where we use all the data that we have, including this historical data from pilots from devices we have encountered before. And we would pull all this data together to define a larger data set, and we would minimize the cross entropy loss on that larger data set. And so pictorially, what we are doing is we are trying to find a demodulator, a parameter phi, that is not too far from the optimal demodulator parameters for each one of the devices that we have observed before. Right? So this phi, this phi1, phi2 are, I thought I turned off this. Okay, let me just shut this down. So the we want to find the model parameters phi joint that are in some way close enough, as close as possible to the optimal individual demodulators for each individual device. And again, this may not be possible. So this joint model may be quite far from the optimal demodulators that you would want to use on each individual device, on each individual channel configuration. And so this implements the joint training block diagram that we have seen earlier. Now let's get to meta-learning. So in meta-learning, we have two types of parameters to worry about. There is the shared hyperparameters theta that defines the inductive bias. So this theta, for instance, identifies the training procedure that we are going to follow for adapting to the data of each task. And then we have for each task, here for each device, we have a device-specific parameter. And the idea is that we're going to meta-learn the hyperparameter, the inductive bias, but we're going to use conventional learning based on the meta-trained inductive bias to obtain the device-specific parameters. And so formally, one can define a model that encompasses the shared hyperparameters theta and this per device or per user or per task parameters phi within a probabilistic graphical model, a Bayesian network, if you've seen these type of things before, where for each user and for each pilot, we have the pilot, the received signal, and the demodulator is going to depend on both this parameter that is specific to each user, task-specific parameter, and on the hyperparameter. And a principled way to train, to meta-train, to solve the meta-learning problem would be to use expectation maximization, right? Because we have these latent variables and we have these hyperparameters that affect all the latent variables. And so we could use, again, expectation maximization to solve this problem. The issue is, of course, that in practice, expectation maximization is of prohibitive complexity because one needs to infer, do optimal Bayesian inference of these latent parameters. And so this is typically not done. And all the meta-learning algorithms really are, in one way or another, approximating the way expectation maximization would optimally solve this problem. And then if you're familiar with expectation maximization, you know that it works according to a nested loop architecture. And so all the meta-learning algorithms that I'm familiar with have, inherit from EM, from expectation maximization, the same nested loop architecture that can be described as follows. So we have, again, an inner loop and an outer loop. In the inner loop, we fix the inductive bias, so the training procedure, theta, the hyperparameter theta. And fixing that, we update the device or the task-specific parameters for a subset of the tasks in the meta-training data set. Okay, so in the context here, we take data from a number of meta-training devices. Based on the current inductive bias, we train demodulators for each one of them. Okay, and this is what we do in the inner loop. We apply conventional machine learning, starting from the current inductive bias, separately for each one of these meta-training tasks that we have selected. And then, as you can imagine, in the outer loop, what we want to do is we want to update the hyperparameters, the inductive bias, in such a way that the performance of the models that we trained in the inner loop is maximized. Okay, so we want to improve the inductive bias so as to enhance the performance of the adaptation that takes place in this inner loop. And so in the inner loop, what we have is we have conventional training going on in parallel over multiple tasks. And in the outer loop, instead, we update the inductive bias in order to improve the operation within the inner loop. And to be concrete, let's see how, and again, I think most of the meta-learning algorithm follows this structure in different ways. And one of the most prominent examples is MAML or MAML, which stands for Model Agnostic Meta-Learning, that famous paper that I pointed to earlier in the talk. And so as applied to our problem, MAML works as follows. So remember we have the shared parameter theta, the hyperparameters, and then the model parameter, the specific to each task, which are phi. So with MAML, as applied to our problem, the demodulator is defined by device-specific parameters. So for each device, for each task, we have a classifier that has weights that are specific to that task, to that device. What is shared is the initialization that we use in the inner loop to update the model parameters, to update the parameters of the demodulator. Okay, and so the way this works is that, again, in the inner loop, we select a few of the devices from the meta training data set. We start from the same initialization point, which is the current inductive bias, the current hyperparameter. And starting from that point, we do a few steps of SGD to minimize separately for each meta training task that we have selected, to minimize the training loss. Okay, so we adopt separately for each meta training device the model parameters. We do this in parallel, but starting from the same point. And then in the outer loop, we choose the hyperparameter that maximizes or minimizes the loss after adaptation that we have observed in this inner loop. So we want to find the hyperparameter theta that minimizes the sum of the losses that we get after adaptation, after we apply SGD from this starting point. And importantly, in the inner loop, we need to use training data for each task, because our goal is to train, again, to train separately for each meta training task. But in the outer loop, because we need to evaluate the performance of that adaptation, we need to use test data for each task. Because again, we need to check how well the procedure generalizes outside the training set. So one way to think about is what we are doing with meta-learning is that we are learning how to optimize. So we are learning how to optimize in the sense in particular of choosing a suitable initialization, where the goal of the optimization is the generalization loss, is the test loss. So pictorially, while joint learning tries to find a point that is somehow in between all the optimal model parameters, MAML tries to find a point from which we can reach the optimal parameters for each one of these meta training tasks with a few steps of adaptation. So while the joint approach does not account for adaptation, meta learning builds as built in the fact that there will be adaptation occurring on task-specific data. And so in this case, you just try to find an initialization that allows you to quickly adapt. And so the only question that is left here is how we actually do the update in the outer loop. And so remember, we want to maximize the performance after adaptation. And so as usual, we'd like to use gradient descent, so first order methods. And so we need to try to figure out what is the gradient of the loss that you observe after adaptation for these K meta training tasks we have selected. And so we need to see how much, if we move a little bit the hyperparameter, how the loss measured after adaptation changes. And you remember that the relationship between the initialization and the adaptation, the adapted model parameters, one for each task, is given by the gradient of the training loss. So the relationship between this point and this point is given by a few steps of gradient descent. And so if we want to differentiate the losses measured here with respect to this point by using the chain rule, we need to differentiate through this gradient. So we need to basically compute the gradient of a gradient, which yields the Hessian, right, the second order derivative of the training loss. And so MAML therefore requires you to compute the Hessian of the training loss. So it's a second order method in a way similar to, for instance, Newton, Raphson type of scheme. More specifically, what you need to do is to compute the product between the Hessian and the gradient. And in fact, this can be done with a complexity that is double that of computing a single gradient, and approximately. But it's more complex than running conventional gradient descent. And so there are various schemes that try to simplify the process. So one is proposed also in that original paper. And essentially what they said is, well, let's just remove this Hessian because it's too onerous to compute. There is no good justification, I think, theoretical justification for it, and it doesn't quite work so well in practice, but it's definitely a reasonable thing to try. There is another scheme that somehow seems to work better in some applications, which is known as REPTILE. REPTILE essentially works as follows. The hyperparameters are updated using as a delta, right, as the update, the average of the updated model parameters. So you calculate the updated model parameters, you average them, and then you use them to update the hyperparameter. There is some justification in the original paper as to why this is really akin to meta-learning. It is not very clear to me, but one thing that is striking if you are familiar with this literature is that this is the same as federated averaging, right? Because if you think of these tasks at different devices, and each device, you know, and this theta is the parameter that you download from the server in federated learning, then these are the updates that each device does locally. And then these updates are sent to the server, and the server just averages them. Then you see that this is exactly the same rule. And so, you know, there is a tight connection between meta-learning and federated learning. And this is in this case, it's just in terms of this particular algorithm, but you know, I think the connection goes deeper than just this particular algorithm. There is also another scheme that we have used in our simulations. I'll just briefly mention it. It's known as CAVIA. So here, the idea is that, you know, remember in MAML, the weights of the demodulator were adopted, right? So we started from the same point, and then we adopted the weights of the demodulator. In CAVIA, instead, we fix the weights of the demodulator in the sense that these are shared. All the devices use the same weights, which we you know, share across multiple devices. But what is adopted is an additional input vector that you include in the, input vector, this one, that goes inside your demodulator. So the demodulator takes as input the received signal Y and outputs all those probabilities. And now it has an additional input vector, which we adapt to the current task. So in a way, this is the opposite of MAML in the sense that the weights of the demodulator are fixed and you only adopt this input vector. And as maybe it's clear from this discussion, there are so many other algorithms one could consider to implement meta-learning. And in one way or another, as I said, there are some more sophisticated approximations of EM. For instance, in some cases, you also want to, instead of using point estimates, you may want to use more refined posteriors for the local parameters and so on. And then, you know, there is really a lot to study and a lot to contribute to also, I think. Okay, so let me just then show an example of how this works in practice for this simple setting that I've been using to describe the approach. So let's consider now again our uplink channel, and let's say we are using 16 QAM, and let's also assume that each device has a random IQ imbalance that in this setting we assume it's difficult to model, so we don't try to model it. We try instead to use a data-driven design approach. But again, the way we simulated this is that we have random IQ imbalances that imbalance the powers on the I and Q axis of the constellation. So the different tasks are defined by different such randomly generated imbalances. In this plot, I showed the symbol error rate for 16 QAM uncoded transmission versus the number of pilots that we have for the new device, for a new device that comes in. For the meta training devices, I think we use 4 pilots. So we had 4 pilots for any of the other meta training devices, but we let the number of pilots for the current device vary. This one at the bottom is what you'll get if you assume that you know about the IQ imbalance, you know the channel, and you just design the optimal demodulator, which is quite easy to do because it is 16 QAM. The one you get on top is if you ignore the presence of that imbalance and you just assume that the channel is linear and you just use the conventional approach, it doesn't perform quite as well. This is what you get if you use conventional learning, where you train from scratch for the new device. And of course, it can outperform the scheme that ignores the presence of that IQ imbalance, but it takes quite a few pilots to converge to the optimal demodulator. This is what you get if you use joint training, very poor performance, because there is no single demodulator that works well across all possible different realizations of that imbalance. And this is what you get if you use meta-learning. These are different schemes that I mentioned before, CAVIA, REPTILE, and MAML. And the bottom line is that, as promised, with just a few pilots, you can more quickly get to decrease the symbol error rate, and so much more quickly than conventional learning, and you can definitely improve over the conventional scheme. And so this indicates that it's a very simple example, but it indicates again that we can significantly improve the sample complexity, the number of pilots that we need to train a demodulator. And of course, similar discussions would apply also to train decoders, and there is also some work around that. One interesting question is how many meta-training devices you need to observe, right, before deploying the system, before you can trust the inductive bias theta that you have, the initialization that you have meta-trained. This is an interesting question that we have also studied theoretically using information theory. We have some work on this subject. And here I'd just like to show one particular numerical result. So here again, symbol error rate versus the number of meta-training devices, each one giving us 4 pilots. And the reference curves are the same that we have seen before. Again, joint training fails for the reasons that I've explained. And here you see the performance with meta-learning, which indicates that, yes, you need to observe a sufficiently large number of meta-training devices before you can trust that the inductive bias that you have obtained would be biasing learning in a way that it would improve over a random initialization and conventional learning. You see that we cross this line after we observe a certain number of meta-training devices. The last thing I wanted to mention here, and hopefully then there will be some questions, is that I have presented meta-learning as implemented in an offline fashion, where somehow one collects this data offline, obtains this hyperparameter, and then uses it online to adapt to each new configuration that is observed. But of course, this can be done in an online fashion, right? In this example, as we observe pilots for more and more devices, we can build up a meta-training set that we can use to constantly refine the inductive bias, so to constantly improve the way we adapt to new situations that we get to encounter. And of course, by doing this online, we can also hope that the system would work in non-stationary situations in which the statistics of the system may change over time. And this type of approach is known as online meta-learning and also as lifelong learning, right? Because as time goes on, we change the way in which we adapt to new circumstances. So lifelong learning.
Hey, Osvaldo?
Yes.
Just on that last example that you did, the channel model was really fading, but was it just for a single realization of the channel? Is that the idea that this adaptation is to a single realization, or are you having new channel realizations every some coherence time or something like that? So
yeah, so this one is it's the simplest possible scenario where we get pilots for a new channel realization and a new realization of these IQ imbalance variables, and within that coherence time, we get to observe a few pilots, and that's it, and then data.
Okay, so this is for coherence time, basically.
Yeah. So for a single coherence time, we get some pilots, we decode, and then we observe another device.
Okay.
Does it make sense?
Yeah. So I mean, so here, okay. Oh, it's just for the meta test. Okay.
Okay. Okay. Now, if it wasn't clear.
Yeah. Yeah.
Okay. anyway, we can discuss it further because I'm actually done. So yeah, so we can use all lifelong learning, right? As we go on, we keep changing our hyperparameters. And so if we keep track of how well that hyperparameter allows us to adapt to new channel realizations, to new configurations, and so on, we can also adaptively allocate more or less resources for adaptation. So for instance, if you have observed that your current inductive bias allows you to estimate the channel or estimate a demodulator with just a few pilots, maybe the next next time you schedule a transmitter, you tell the transmitter to transmit fewer pilots, because you know that you have obtained a suitable inductive bias for the current propagation environment, and this can be adapted online. And so we have come up with some particular way of doing that, and the bottom line, of course, is that this can reduce the average number of pilots that you need, again, by adapting the resources you allocate for adaptation depending on the quality of the inductive bias that you have meta-learned so far. Okay, and yeah, this brings me to the end. As I promised, this was quite high level. The main message is what I mentioned at the beginning, that meta-learning, as opposed to conventional machine learning, provides a more general framework that includes conventional machine learning as a special case. And the main goal of meta-learning, as we have seen, is that to learn how to adapt. And in so doing, one can hope to solve or to limit two of the critical limitations of machine learning for communication systems, namely the fact that we need a lot of data anytime the system configuration changes, and the fact that we need to retrain the system to spend complexity, compute time, anytime the system configuration changes. I've also hinted at the fact that because we have this new level of adaptation at the level of hyperparameters, this may lead to different ways of allocating resources to a new forms of adaptive resource allocation that leverage this knowledge. And as I mentioned, I only provided here some experimental results, but we also have some information theoretic analysis of meta-learning. And as you're probably familiar, there are many other potential applications of meta-learning, and here I'm just mentioning some of them. And this is really everything. Thank you very much.